For decades, if you got a donor liver, its journey to you was basically a race against time in a glorified cooler. Seriously, an icebox. But what if you could change that? What if you could take that organ, hook it up to life support, and actually make it healthier before it even gets to the recipient? Well, today, we're going to break down the incredible machine that's doing exactly that.
All right, so here's how we're going to break it all down. First, we'll look at the race against time surgeons have been running. Then, we'll get into the machine that's changing the game. Think IceBox versus life support. We'll explore the two different temperatures it can use, check out the solid proof that this thing actually works, and then we'll look ahead to the future, and it is wild. Think organ repair centers. Let's get into it. Okay, first up, a race against time. You know, to really get why this new tech is such a huge deal, you first have to understand the massive problem that doctors and patients have been up against for a long, long time.
So a lot of donor livers these days come from something called donation after circulatory death, or DCD. Now, this is different from donation after brain death. With DCD organs, the heart has stopped, which means there's a period where the organ isn't getting any blood flow, while it's still at body temperature. And you can probably guess, that warm ischemia time, as they call it, makes these organs super fragile and way more prone to injury.
And for decades, the way we've dealt with this is, well, pretty basic. It's called static cold storage, or SCS, and it's exactly what it sounds like. You flush the liver with a cold solution and pack it on ice. That's it. It's like putting a steak in a cooler. Sure, it slows down the decay, but that's all it does. It's totally passive. It doesn't stop the damage, and it definitely doesn't do anything to fix the injury that's already happened.
And here's the real kicker. This whole IceBox method, especially for those really sensitive DCD livers we just talked about, comes with a massive risk. We're talking about a severe complication where the tiny, delicate bile ducts inside the liver get damaged. It's called ischemic cholangiopathy, and it's bad news. It can actually cause the brand new transplanted liver to fail.
So you've got this huge challenge, right? You're either forced to throw away precious organs, or you risk the health of the patient. Faced with that, scientists and doctors knew they needed a whole new approach, a new philosophy, really. And this is where things get really interesting. It's a total shift in thinking. We're going from the passive IceBox to an active portable ICU. Imagine that. Instead of just slowing down the organ's decay by chilling it, this machine actively keeps it alive outside the body. It's pumping it full of oxygen and nutrients. And this changes everything, because now you can actually assess how healthy the organ is, and maybe even repair it. Now, there are a couple of ways to do this. There's what they call in situ perfusion. That basically means in place. It's done inside the donor's body before the organ is even recovered. But then there's ex situ perfusion, out of place, and that's what we're really going to dig into. This is where the liver is removed and then hooked up to this dedicated machine. Okay, so we're focusing on the portable ICU, the ex situ machine. But here's where it gets even cooler, or warmer, depending on the situation, because it turns out the temperature you run the machine at totally changes the goal of what you're doing. So that leads to a pretty big question, right? Once you've got this liver hooked up to the machine, what do you do? Do you keep it cold, kind of like the old IceBox method, or do you warm it all the way up to body temperature? And the answer is, it depends on what you want to do. It's not about one being better than the other. They have totally different jobs. So if you run the machine cold, that's hypothermic perfusion, your goal is repair. At that low temperature, the liver's metabolism is super slow, so its cells can focus on replenishing their energy stores and fixing themselves. But if you run the machine warm, that's normothermic, your goal is testing. You're basically tricking the liver into thinking it's back in a body. You can see if it's working properly, making bile, clearing out toxins, proving it's actually viable for transplant. So you've got one method for repair and one for testing. The obvious question is, why not just do both? And that's exactly what the most cutting-edge approaches are doing now. It's this incredible sequence. First, you start cold with something called DHOP to repair all that initial damage. Then you have this very slow, controlled rewarming phase so you don't shock the organ. And finally, once it's at body temp, you switch to warm perfusion, or NMP, to test it out. It's brilliant. Repair it first, then test it to make sure the repair worked. All right, this all sounds amazing, almost too good to be true. But theory is one thing. Does it actually work in the real world? Does it lead to better results for patients? Well, let's look at the proof. The big answer, The definitive proof came from a huge study published in one of the world's top medical journals, the New England Journal of Medicine. It was called the DO-PEACH DCD trial. And what they did was put this technology to the ultimate test. They took those high-risk DCD livers and randomly assigned them to either the old-school IceBox or to cold machine perfusion. And the results were, honestly, they were jaw-dropping. You remember that really nasty bile duct complication we talked about, ischemic cholangiopathy? Well, in the IceBox group, 18% of livers developed it. 18%! In the machine perfusion group, just 6%. That is a massive difference, a 2/3 drop in the biggest, scariest risk for these kinds of transplants. But wait, there's more. It wasn't just about long-term problems. The study found a whole bunch of other benefits. The machine-perfused livers worked better right from the get-go. They caused less shock to the patient's body when they were hooked up, and they just functioned better immediately. So it's not just that they were safer down the road. They were literally healthier from the very first minute inside the recipient.
So, the proof is in the pudding. The evidence is crystal clear. We can now take a liver, keep it alive outside the body, repair it, and then test it. This is a total game changer, and it's opening the door to a future that frankly sounds like something you'd read in a sci-fi novel.
So think about this. The whole paradigm of transplantation has been a frantic race against the clock. But now we can imagine something totally different. We can imagine dedicated organ repair centers. Seriously, just picture an ICU, but instead of patients in the beds, you have organs. Livers, kidneys, hearts, each one getting stabilized, treated, and maybe even upgraded before it goes to a person. And check this out. This isn't just some far-off dream. This stuff is being worked on right now. We're talking about taking a fatty liver, which might have been discarded before, and defatting it on the machine, or curing a liver of an infection like hepatitis C before transplant. What about using anti-aging therapies to make organs from older donors function like younger ones? Or even using gene therapy like CRISPR to fix genetic defects? And the Holy Grail? Maybe one day, using enzymes to strip away blood type markers to create a universal organ that anyone can receive. It's incredible.
So you see, this machine, it's not just a slightly better cooler. It's a platform. It's the foundation for a whole new way of practicing medicine. It takes organ preservation from this desperate race against death and transforms it into a window of opportunity. An opportunity to heal, to improve, and to save more lives. It really makes you wonder, how far can we push this? What's the limit? Could we one day engineer the perfect rejection-proof organ before every single transplant?